Take a look.
When we go there.
All right, guys, page 24. This is the last new topic before we do test review. So let's just do a little bit of review with log values. So a couple important values to know. Natural log of 1. If you guys remember, what's natural log of 1 equal to? 0. Yeah. What about natural log of 0? It's not 1. Here's what the natural log graph looks like. What's happening on the y-axis? Vertical axis. So natural log of 0 is the 5. E to the 0. Yeah, anything raised to 0 is 1. Yeah. Remember, E and natural log are inverses of each other. E to the natural log of A, just A. Yeah. So E and natural log cancels out, and the natural log of E to the A is also A. This is using log properties, power property. If I have a natural log expression or log expression, that exponent can be free to move. And then I know natural log of E is equal to 1. So yeah, that's equal to. So all these, we're going to revisit all of the old derivative rules, but basically all the new ones, I'm going to have chain rule built into them. So we have derivatives of exponential functions. E to the u, this is the one that we know, which is just the original function, e to the u times u prime. If I have a to the u, this could be like a function where my base is no longer e, so like 2 to the x, or 3 to the x, or 8 to the x. They all follow this a to the u rule. It looks a lot like e to the u in the sense that it's the original function times the exponent's derivative. But there's a conversion that needs to happen. So there's a natural log of a. Think of that as a conversion into base e. And then the rest of it looks a lot the same. It's the original function. So original function is a to the u times u prime. So e to the u and a to the u are virtually the same process. It's just that a to the u is not as clean because it's not base e, so it needs to convert into base e before we jump into the rest of the rule. So a quick example here. Find f prime if f of x equals 2 to the x plus 3e to the x. So 2 to the x falls under the category of an exponential function base a. So f prime is equal to, now think of 2 as base a. So what comes first? Yeah, ln of 2 times 2 to the x, yeah, the original function, times 1. Yeah, in this case, we look for chain rule, but there's nothing besides x. So, but it's always good to look for that chain rule portion, even if it's just x, because, you know, at worst, you're just putting a 1 here. Plus, and then e to the x follows e to the x. So 3e to the x is just what? 3 to the x. And then it's really times 1, but you don't have to do it because you know that's not going to do anything, not going to make any changes. So plus 3e to the x. Just understand that this 2 and this 2 are not compatible. This 2 is inside natural log, so we can't make a natural log of 4. Okay, so this is, think of this as just some coefficient. It's just some number hanging out in front of 2 to the x, just like that 3 is. It's just in a more, it's not going to be a nice integer value, so we leave it as natural log of 2. Anyone's phone? Log functions. We learn natural log of u, which we learn natural log of x, which is just 1 over x. But if there is chain rule component, it's going to be the 1 over x times the inside function's derivative. So if I merge it together, I'm going to say it's u prime over u. Or you can think of it as 1 over u times u prime. But I typically write it this way, but you can write it this way as well. Log base a of u. This is base other bases other than e. So base 2, base 3, base 5. Okay. There is a conversion component that needs to happen in front, and it ends up being 1 over natural log of a. But then the rest of the rule looks exactly like natural log of u. It's just u prime over u. So anything dealing with base a, whether it's exponential or logs, will require a conversion. But for a to the u, the natural log of a is in the numerator. For log, the natural log of a is in the denominator. Okay, so it says find f prime of x for the function log base 4 of x minus 4 natural log of x. These are both log functions. One is base 4, the other is base e. So log base of 4, there's conversion that needs to happen. So 1 over what? Yeah, 1 over ln of 4. Think of that as just some numeric value that has to hang out in front. U prime over u. So times what? Good, 1 over x. Minus the 4 is the coefficient that stays. And then what's natural log of x's derivative? 1 over x, yeah. You leave it like this, you can clean up. Doesn't really matter. All right, go ahead and try 1 through 3. Oh, sorry, I messed up. That should be a 1. 1 up top. All right, 1 through 3, these are a mixture of different rules, including some trig rules as well. But see if you can identify the rules and apply them. So try 1 through 3. Yeah.
On question 3, did you get contact with the or like?
No, it's fine. Just understand that the 2 and the x are not compatible, so I typically like to put the x in front of the natural log of 2 so that it doesn't get mixed in with, it doesn't get interpreted as natural log of 2x. But yeah, you don't have to clean up. All right, I have one more new topic to go over, and that is called log differentiation. Page 25. So log differentiation is where we simplify a function that has no logs in it. It's a non-log function using log properties to expand before differentiating. The reason that sometimes we want to do this is because log properties allows us to, well, if something is within a log expression, we can basically split up into smaller pieces, into smaller problems, either using product property or using quotient property. And sometimes we introduce logs into the problem so that we can take something that is very condensed and split them up into individual pieces. And if we do that, then every derivative feels easier to manage. So there are 2 cases where we may want to do log differentiation. One where you want to try to avoid a combination of product, chain, quotient, rule, all kind of meshed into one problem, basically splitting up a really messy problem into easier parts. And then the other scenario is where you have a variable raised to a variable where we don't have a rule that can handle this explicitly. So we use log differentiation to force it into something that can be manageable. So example 1, if you want to find the derivative of this function, normally you have to go through quotient, and within quotient, you have to go through chain rule for the top and the bottom. And with log differentiation is where we start off with introducing logs into the equation. Anything we do to one side, we can do to the other side. And I'm just forcing that denominator to be rational exponent. So now that I'm inside a log function, I can take advantage of log properties. So this is now in the form of natural log of a over b. And if I have natural log of a over b, I can expand into the difference of 2 logs. So natural log of x minus 2 quantity squared minus natural log of x squared plus 1 to the 1/2. And at this stage, we could find the derivative, but we can bring the exponents down as well because there's also power property that allows us to bring the exponent down, and that will simplify our derivative process. We can avoid chain rule. So we're going to bring the 2 and the 1/2 down. So we're still in the cleanup stage here. So now these individual pieces are a lot easier to find the derivative than having to go through product, chain, quotient, or in this case, quotient and chain. So now we just have to apply u prime over u for both of these. And then there's a little bit of implicit because there's a y now. Before it was by itself, but now y is stuck inside natural log. So we've got to keep track of our dy dx. So within each term, we're just going to find the derivative. Remember, the natural log of u's derivative is u prime over u. So the derivative of y is 1 over y dy dx. Next up, remember, we can't distribute the natural log through, right? So this is kind of stuck within each part as the u value. So 2 is the coefficient, and then u prime over u. What's u prime over u for my natural log expression? 1 over x minus 2, okay. Minus, coefficient stays. Also u prime over u. Numerator becomes 2x over x squared plus, yeah. The final step, or we're getting close to the end here. We just want to solve for dy dx. So I want to multiply y to the other side. So this y is going to end up in the numerator on the other side because I'm just going to distribute a y through to the other side because my goal is to just try to get my dy dx by itself. I'm just going to clean up my fraction as I don't have to, but I'm just going to clean up as I go along. But if you don't, it's not a problem. Now, we started with a function, so we should be able to represent our derivative with only x's. So what can I replace this y with? The original, yeah, the original expression. Now, when you go through log differentiation, everything is going to feel messier because we've done a kind of a sprawled out version of the derivative, but just know that you don't have to clean anything up. As long as you have a derivative that's equivalent to a reduced version, you won't get any, and you're not expected to do common denominator with these types of problems. The derivative is messy, but it's easier because we're able to take everything into separate pieces and then find the derivative. So for a problem like this, if there were no instructions given except to find the derivative, then you can either go through a combination of quotient chain or log differentiation. But you won't be expected to do log differentiation unless I specifically tell you to use log differentiation, right? Because this is not the only path to go down. Now, having said that, example 2 is a problem where log differentiation is the only way to go about this, because if you look at this problem here, this is a variable raised to a variable. We have a rule for a variable raised to a constant, which is power rule. We have a rule for a constant raised to a variable, which is exponential e to the x or 2 to the x, a to the u. But we don't have a rule that can handle a variable raised to a variable. So in order to force this to look a little differently, so that because we don't have a rule that can handle this, we take the natural log of both sides to get that exponent to live in a different spot. So this one, we have to use log differentiation. There's no other way. Because this is a variable raised to a variable. So let's start off with our equation. I would protect that 2x plus 3 with a set of parentheses. And now we're going to take the natural log of both sides, which will allow for that exponent to move to a different spot to open up some options for us. Okay. Now that we're inside a log expression, we can move that 2x plus 3, right? We have power properties. So that 2x plus 3 comes down. Again, leave it in the set of parentheses. Everything is as expanded as we can make it. And then we can go through our derivative. The left side is going to experience a little bit of implicit. But the right side, can you tell what we have to involve. Product rule. So whenever you do a log differentiation with a variable raised to a variable, you're always going to be expecting product rule to show up. Because that variable is going to now come down and it's going to become, instead of a variable raised to a variable, it's going to end up being a variable times a variable. And that's always going to end up forcing you into a product rule situation. So just be aware of that. Okay, so go ahead and try the rest of it and I'll work through the same time you guys try it. Any variation of this answer is fine. We just need that y to be converted back in terms of x. Okay, any questions? So again, there's two scenarios for log differentiation. One is where you don't have to use it, but it's a good way to avoid a messy combination of product, chain, and quotient rule. If you can split up a problem that's condensed into an expression into multiple log terms. And the other scenario is where you have to use log differentiation because we have no other choice. There's no other rule that can handle a variable raised to a variable. But if you do that, if you do log differentiation, just expect product rule to show up every time. Okay, before we look at some of these practice problems, if you can turn to page 32, I would like for us to look through all of these derivative rules that we've learned. And this is the filled in key page. So I want us to kind of go through this, and then you're going to study it, and then you're going to, on your first try, you're just going to try to fill out this blank sheet. Okay. If you're, I don't expect you to get everything right the first time, but I just want us to attempt it. And then each day we'll get a chance to practice it. I mean, we have a test coming up on Tuesday, but we have today, tomorrow, Friday, Monday to review. So I think, in a couple of days, I think you'll get it all down. But these all have a chain rule built into it, and that's how I want you to memorize these rules. I think if you have the chain rule built into it, you're always looking for it, and I think that's even if it's not there, I think it's always good to just memorize all these rules with that chain rule component. So derivative rule, I have n times u to the n minus 1 times u prime. So imagine if that u was a parentheses with terms inside. We're always looking for that inside portion's derivative. With trig derivatives, we have the sine, tangent, secant, cosine, cotangent, cosecant lined up. Instead of just cosine of x, now we're just doing u times u prime. So all of these is just u times u prime. I think these are the most challenging ones involving log base a, involving this natural log of a in front. But I lined it up this way where we know that if you know that natural log of a and log a, these are both natural log, these are both log expressions. They're both producing u prime over u. It just needs a little bit of conversion for log base a of u. And then e to the u and a to the u are virtually the same idea. If you can just say it's the function times the exponent's derivative, then it's virtually the same thing, right? Original function times exponent's derivative, original function times exponent's derivative, and natural log of a in front. Maybe sometimes students have a little bit of trouble remembering, wait, does the natural log of a go in the numerator or does it go in the denominator? What helps me remember it is if I look at the original rule here, there's a divisional component in my derivative, and that helps me remember that the natural log of a goes in the denominator. Here, the a to the u times u prime doesn't have a denominator component, so that helps me remember the natural log of a goes up top. So maybe that helps you remember where the natural log of a goes, whether the denominator or numerator. And then finally, the arc trig derivatives. Again, I like to start off looking at patterns here. So the way I remember it again is I know that it's only these three you have to worry about. These are the three unique ones. They all have u prime in the numerator. Denominator is all combination of 1 and u squared. So I start off with 1 plus u squared because that's the easiest. And then I go to the most difficult one, the arcsecant. I see the absolute value of u. I know there's a square root, but then sometimes I don't remember, is it the u squared minus 1 or is it 1 minus u squared? And I know it's u squared minus 1 because the u's are next to each other. And if I can figure out this pattern, then this pattern feels easier to figure out because I know it's going to be a little bit different than that. So it's therefore 1 minus u squared. And if I can figure these out, then I can just put a negative in front of all these for these three. Okay, so can we just spend 2 minutes just looking over this? And then I'm going to have us start and try fill out 33. Again, no pressure. If you don't get everything right, it's not a big deal. I think it's just good for us to see, what we know and what we don't know. But just spend a minute looking over it and don't start page 33 until you've had a few minutes to look over it. Okay, go ahead and start. See how much you can do. Page 33. Okay, check over your rules. Look at how you did. Let me start up here first. Okay, turn to page 26. All right, start with number 1. Can I use log properties for natural log of x quantity squared? Is this the same as this? Or not? Okay. This you can bring the 2 down and have an easier time with it. This one, you can't bring that 2 down without changing the overall value. You got to go through chain rule here. So this one is chain rule, and this one is power rule. So number 2, it looks like we have to go through a product rule, but the second portion can clean up, right? What does that turn into? Just x cubed. And these can merge, and my derivative is just a power rule away from my derivative. Number 4, find the rate of change of y with respect to x when x is equal to 1. So it's basically asking for dy dx. We could go through a combination of chain and product, but what can we do with natural log of xy that can allow us to avoid some messier rules? Before we do derivative, do we have a log property that can allow us to expand this? And that way, we still have to go through implicit, but we don't have to go through a whole combination of chain and product, allowing us to avoid it. But we do need ordered pair at 1. So I'm going to plug 1 in for x and solve for y at this stage here. You know, natural log of 1 is 0. So you know y must be equal to e. So we have 2 values that will help us to plug in when we find dy dx. Okay, so now I can find the derivative. Natural log of x, natural log of y.
How did you get y equals e?
Oh, natural log of y is equal to 1. So natural log of what value will allow this to be equal to 1? So natural log of 1 equals 0. Natural log of 0 is undefined. So natural log of e is equal to 1. So we just kind of do a little guess and check here. Some properties to figure out that y is equal to 1. Okay. Right, so to solve for dy dx, we have 1 for x, we have e in for y, and we can just plug in and try to see if we can figure out what that equals to. Okay, try number 5. So anytime that you can take advantage of log expansion, that could simplify the derivative process you have to go through. Okay, so your homework, just page 26 to 29, 1 through 12 all. We've done half of it. So we just have a few more problems to finish up. And then tomorrow I'll give you the test review and we'll begin working through our test review. Help session Friday morning and Monday morning. Your test will be on Tuesday, but no help session on Tuesday because my AP students are also having a quiz on Tuesday, but I'll do a full help session on Monday, and then I can also go over problems on Friday as well. I have your quizzes graded, so I will put them in the gradebook today, and I'll give them back to you. If not tomorrow, I'll give your quizzes back to you by Friday.
Yeah, there was like.